Hi everyone, welcome back to Dave's Math channel. This is my 14th and this will be my last video in my sub-series on derivatives of my series on first year calculus. And today I'm going to derive the formulas for the derivatives of all 6 inverse trigonometric functions, which are written down here. Let me show a bigger copy of the slide. Here they are. So these are the formulas I'm going to derive today. And some of these you very rarely are going to see. I mean, I think the two that are most important on this slide are the first two. The derivative of the arcsine and the derivative of the arctangent. You'll notice something interesting, actually, if you look at these formulas. Look at the formulas on the bottom and compare them with the formulas on top. Notice that the formulas on each column are the same except for a minus sign in the versions on the bottom. So the derivatives of the co-functions are just the negative of the derivatives of the corresponding functions. So that's easy to remember. And the third of these formulas, the derivative of the arcsecant, this is something you're very rarely going to see. So that's probably not worth memorizing. But the first two probably are. But you should know how to derive these anyway. So let's do that. Before I do that, I think it's a good idea for me to show you graphs of all these inverse trig functions. They're really just kind of the same looking graphs as the graphs of the corresponding functions, except reflected about the diagonal line y equals x. That's true for every inverse function, but that doesn't completely define them because we still have to restrict their domains. I mean, if we couldn't reflect the entire, for instance, we couldn't reflect the entire sine function about the line y equals x because that's not a function. I mean, it is a relation, but it's not a function. It's going to go infinitely many far along the y-axis. It's going to oscillate to the left and the right. You know, a function can't do that. So you have to pick out a portion of that that's a function. And the most obvious choice in the case of the arcsine is going from let the domain go from -1 to 1. And then or let the range go from minus pi to pi. You have to define the range to get the inverse that you want. And then for the arc's cosine, you let the range go from 0 to 2 pi. I mean, these are a little bit arbitrary definitions. For the arctangent, it's pretty obvious what the obvious choice is. You just take the branch right in the middle, kind of like you did for sine. And similarly for our cotangent, you just take the branch that's immediately above the x-axis. For arcsecant, it's pretty easy. You just take the branch in the middle. And for our cosecant, you kind of prop it up the way they show here. So anyway, those are the what they look like. And actually, I guess they did arcosecant in the middle, then they did arcsecant. I'm not sure why they did it that way. But anyway, those are what the inverse trig functions look like. You probably learned this in high school at some point. But now we want to derive formulas for derivatives of each of these functions. How do we do that? Well, we use the inverse rule. We can use the inverse rule on each of these. So let's do it first for the arcsine. And remember, the inverse rule just says the derivative of the inverse of a function is 1 over f prime of the f inverse. Well, all we need is f prime and f inverse. And if f of x is sine of x, then f prime of x is cosine x, and f inverse is the arcsine of x. So you just plug it in. And when you do that, you get 1 over the cosine of the arcsine. And you can be a little clever. If you don't remember the formula for the cosine of the arcsine, I don't think it's worth memorizing that. It's easy to derive. Just remember that cosine is just plus or minus the square root of 1 minus sine squared. That just comes from the identity sine squared plus cosine squared equals 1. So we have an ambiguity about the sine, which we usually do when we take a square root. So, but the sine squared of sine inverse, the sine of sine inverse of x is just x, so sine squared of sine inverse of x is x squared. So when you're done with this calculation, you get plus or minus 1 over the square root of 1 minus x squared. And to get the sine, S-I-G-N, All you have to do is remember that, I mean, just look at the graph of the arc sine and notice that it's increasing throughout its domain, which means that its derivative has to be positive. So that means you have to take the plus sign. So the result is the derivative arc sine of x is 1 over square root of 1 minus x squared. Pretty nice result, and a very useful result, too. Um, you'll find you'll use this a lot, especially when we do integration. Remember, if integration is the opposite of differentiation, so this is going to tell you how to integrate the function on the right. Thus give you an arc sine. That's going to be very useful. And cosine is basically the same derivation. The only difference here, I mean, now we have the derivative of cosine as minus sine, and of course f inverse is our cosine. The calculation is almost exactly the same. You'll notice there's a minus sign that crops up though, because the derivative of cosine is minus sine. So now we get a negative sign in the denominator, and that's going to give us what I call minus plus. You could write this as plus minus. I decided to write it as minus plus just because it's the negated thing of what we had last time. Again, we have to consider the sign, S-I-G-N, of the derivative. And if you look at the graphs, let me go back again. If you look at the graph for our cosine, that's the middle one on top. That one you can see that the arc cosine is decreasing throughout its domain, which means the sign is negative now. So the derivative of arc cosine is the same thing as we had for the derivative of arc sine, except we have a minus sign in front. It's minus 1 over square root of 1 minus x squared. And then the arctangent, this one, you can do all these the same way. And, maybe I shouldn't go through every step, but we're applying the same formula. This time we're going to get, remember the derivative of tangent is secant squared, and we can use the identity that secant squared is 1 plus tangent squared. So we're going to get 1 over square root of 1, no square roots this time. Just 1 over 1 plus tangent squared of arctangent, but the tangent of arctangent of x is x. So in the end, we get 1 over 1 plus x squared. And like I said, this is a very useful formula. This one and the one for the derivative of the arc sine, I think, are the most important ones. So this one is worth memorizing. You will see this a lot, again, when we do integration. So anyway, and then the cotangent, same thing pretty much. I don't think I should go through all the steps here. It's basically the same calculation. And you're left with the same thing with a minus sign when you're done. Kind of cool. So anyway, what about arcsecant? This is probably the most complicated one. And this is one you don't have to worry about too much because you very rarely see this. Arcsecant is a very rarely used function. I don't even know how many times I've actually seen it used. Very, very unfrequently. But anyway, let's just do the calculation. So now we're letting f of x be secant. And remember the derivative of secant x is secant x times tangent x. So now when we do everything, we get 1 over the secant of inverse secant x times the tangent of inverse secant x. Secant of secant x is obviously x. And tangent of arcsecant x is, remember tangent is 1 plus secant is square root of 1, secant squared minus 1. So that we're going to get a square root of secant squared of secant, inverse secant x minus 1. But secant of inverse secant of x is x. So we're just going to get x squared minus 1 in the square root. And we get an extra factor of x coming from the secant of the inverse secant. But we still have an ambiguity about the sign. But then again, if you look at the graph, let me just go back to the graphs again. Yeah, the secant is the one on the lower right. And you'll see that the secant is increasing throughout its domain. It actually has two kind of separate pieces of its domain. It's a discontinuous function, but everywhere where it's defined, it's increasing, which means that its derivative is positive. So so we get the plus sign. And the result, and you have to be a little careful here because x can be negative. Remember, I'm not going to flip back to that graph, but secant is also the inverse secant is defined for negative x as well as positive x, but the derivative is always positive, which means that we have to replace x with its absolute value to ensure that the result is positive. So we get the derivative of the arc secant of x is equal to 1 over absolute value of x times square root of x squared minus 1. Kind of a weird result. And it's not one you really have to worry about too much because you're very rarely going to see this function. This one doesn't come up a lot. So, and if it does, you could just look it up probably. And then it's the same derivation for the arc cosecant. The only difference here is that, again, you get a minus sign because it turns out that the arc cosecant is decreasing throughout its domain. So the result you get is the derivative of the arc cosecant of x is minus 1 over absolute value of x times square root of x squared minus 1. Just the negative of the derivative for the arc secant. So anyway, we've just computed, I think, all the derivatives on this slide. These are all the elementary functions. So now we know how to calculate the derivatives of every elementary function, and you can compose them even, and you can add them and subtract them. We know linearity. We know we can multiply them because we have the product rule. We can divide them. You can do any basic elementary operation on any combination of these elementary functions. That's still an elementary function. And we know how to compute the derivatives of all of them. So now we know how to compute the derivative of every elementary function. And that's really all we care about in this course. I mean, there are other types of functions called special functions, but we're not going to see them in this. And, you don't see them in first year calculus. You might see them I don't think I even saw maybe a third year. I mean, I think you might see them your junior or senior year of undergrad, or maybe not even until graduate school. You don't have to worry about special functions right now. There are some very useful ones like the error function or the gamma function or the Riemann zeta function, but we don't have to worry about those functions here. So anyway, that completes my video, and that completes everything we need to know about differentiation. So we're done with differentiation. So hooray. And we can move on to the next topic. Actually, the next topic I want to talk about is applications of the derivative. Before we go into the opposite of differentiation, which is integration, it might be useful to talk about things like the second derivative and critical points. It turns out that a good application of the derivative is finding maxima and minima of differential functions. Those are what are called critical points. That's a very useful application. So next series we'll talk about applications, and we'll have some fun problems because applications involve problems in the real world. I think so far most of what I've been talking about in this series has been pretty abstract, but in the next sub-series we'll get into some useful applications of differential calculus. So anyway, thank you for watching. Long live math, and I'll see you guys next time. Bye.